All right, let's talk about building better Lambda functions. Today, we're going to take the official AWS best practices and translate them into a super practical, actionable guide. The goal here is to build a mental model for creating serverless functions that aren't just working, but are truly ready for production. Okay, let's jump right in.
You know, it's a really important question to ask yourself. A poorly built function can be a ticking time bomb, quietly racking up costs, failing when you need it most, or even opening up security holes. But a well-architected one, that's a different story. That's a finely tuned machine, efficient, tough, and secure. Today, we're building the machine.
So where do we start? Well, everything, and I mean everything, starts with the code. This is our blueprint. Before we even think about things like memory or scaling, we've got to make sure the code itself is smart and built for the unique world it's about to live in.
And this right here, this is probably the single biggest secret to making your functions faster and cheaper. See, a lot of people think Lambda spins up a brand new environment for every single request, but that's not how it works. The magic is that it reuses what's called the execution environment. And if you know how to leverage that, well, that's a total game changer.
And this shows you exactly how it works. It's a two-part life cycle. Think of the init phase, that's all the code outside your main handler function, as your one-time setup fee. This is where you put the heavy lifting, like setting up your database connections or initializing SDK clients. Then, the invoke phase, the code inside your handler, gets called over and over, reusing all those pre-warmed resources for free. This simple separation is a massive optimization for both speed and cost.
So, building on that, let's cover a few key habits of really sharp serverless developers. First up, don't hard-code your configurations. Use environment variables. It makes your code so much more flexible. Second, use keep alive to maintain your connections. You don't want to be reestablishing them over and over. Third, write idempotent code. And yeah, that's a bit of a fancy word, but all it means is your code can run multiple times with the same input and get the same result. This is crucial for preventing errors if an event gets sent twice. And finally, stick to the public documented APIs. Don't go poking around in the internals because it's just going to break on you later.
Okay, now for a big, flashing red warning sign. A function that calls itself, or kicks off a process that then calls it again, can create a terrifying infinite loop. This is, hands down, one of the fastest ways to get a shocking AWS bill. If you ever see this happening, here's your emergency brake. Go to that function's configuration page and set its reserved concurrency to 0. That will immediately stop all invocations and stop the bleeding.
All right, so our code is solid. It's smart, it's safe. Now it's time to pop the hood and dial in the engine. This is where we get into the function settings to squeeze every last drop of performance out of it for the absolute lowest cost.
So, let's bust a myth right now. This is probably the biggest misconception about tuning Lambda. When you increase a function's memory, you're not just getting more memory. You are also getting a bigger slice of the CPU pie. The more memory, the more powerful the CPU. So the real question is, how do you find that perfect sweet spot where you're not overpaying, but you're getting all the speed you need?
And the answer? It's hiding in plain sight, right inside your CloudWatch logs. After every single run, Lambda prints this little report line. And that max memory use number? That's your golden ticket. If you've given your function, say, 512 megs of memory, but this line consistently says you're only using 50, you're over-provisioned. You're just wasting money. It's literally that simple.
So you've got this classic trade-off, right? It's like the tortoise and the hare. The function on the left, with low memory, costs less per millisecond, but it runs for so long that the total bill can end up being higher. Meanwhile, the high memory function on the right costs more per millisecond, but it finishes in a flash, so the total cost is actually lower. The only way to find your function's sweet spot is to test it out.
Okay, here's a quick-fire checklist for you. Always load test your function to find a realistic timeout. Don't just set it to 15 minutes and forget it. If you're doing heavy-duty math or machine learning, look for libraries that use AVX2. It's basically a free turbo button for your CPU. Be aware of your quotas, like the half gig of temporary disk space in TMP. And finally, do some housekeeping. Clean up old unused functions so you don't hit account-wide limits.
So, our function is a lean, mean, perfectly tuned machine. But what happens when we unleash it into the wild? This next part is all about making sure our function can handle not just one request, but potentially thousands of them, all at the same time.
And here we hit the central challenge of going serverless. Your Lambda function can scale like crazy, spinning up thousands of copies of itself in seconds. That's amazing. But can your old-school relational database handle 1,000 new connections all at once? Probably not. The real test isn't just how fast your function scales. It's how well it plays with other systems that, well, can't.
So how do we deal with that? We build in tolerance, using this classic three-step pattern. First, set aggressive timeouts. Don't let your function hang around waiting forever. Second, if a request fails, retry it. But, and this is the secret sauce, don't just retry immediately. Use exponential backoff with jitter. That's just a fancy way of saying you wait a little longer between each retry and you add a little bit of randomness. That way you don't get a thundering herd of all your functions hammering the downstream service at the exact same millisecond.
And for things like stream processing with Amazon Kinesis, this chart tells the whole story. The number of shards in your stream is what directly controls how many Lambda functions can run in parallel. It's a direct relationship. You want more processing power, you add more shards. Simple as that.
Here's another pro tip for you. Imagine you pull in a batch of, say, 100 records from a Kinesis stream, and just one of them has an error. By default, Lambda would try to reprocess the entire batch of 100 records. But if you enable partial batch response, you're telling Lambda, hey, just retry that one single record that failed. It's a massive, massive efficiency gain.
All right, we've made it to the final stage, and you could argue it's the most important one. Our function is smart, it's fast, it's scalable, but now we need to make sure it's secure and that we have a crystal clear view of what it's doing in production. We need to give it a bulletproof vest and a pair of binoculars.
Okay, let's talk about custom metrics, because the way we do this has totally changed. The old way was just slow. You'd make an API call to CloudWatch from inside your function, which added latency to every single run. The new way, the embedded metric format, is just brilliant. You simply print a specially formatted line to your logs, and CloudWatch picks it up automatically in the background. It has zero performance hit on your function. It's a no-brainer.
All right, this is the question that haunts every cloud engineer's dreams. How do you catch a runaway cost spiral before it shows up as a nasty surprise on your monthly bill? Remember that recursive loop we talked about? How do we find that before it's too late? Well, the answer is machine learning. AWS cost anomaly detection is like having a financial watchdog for your account. It learns what your normal spending patterns look like, and the second it sees something weird, like a sudden massive spike in Lambda invocations, it barks. It sends you an alert, giving you a chance to fix the problem long before you get the bill.
And last but not least, let's arm you with your security toolkit, because you don't have to do all this manually. Think of AWS Security Hub as your automated compliance officer. It's constantly checking your functions against security best practices. And then there's GuardDuty Lambda protection, which is like your on-site security guard, watching the network traffic 24/7 for anything shady, like your function talking to a known malicious IP address.
So there you have it. We've gone through the whole journey, from writing smarter code and tuning for performance, all the way to scaling under pressure and locking down security. By using these best practices, you're not just deploying code anymore. You're engineering applications that are resilient, efficient, and secure. You now have the blueprint for functions that are smarter, faster, and stronger. The only question left is, what are you going to build next?